how can we reduce the complexity of an AI? For instance, if it's too complex, how do we make it simpler? Let's start with the core problem, overfitting, i.e., when the variance is high and the bias is low. In this case, the core cause of this overfitting, this sensitivity, this unpredictability, and the fact that it memorizes the training data and fails to generalize, the core issue of that is that the model is too complex. It could be it's too expressive, or it just is too complex for this data set. Well, think about that. If complexity is the issue, can't we just solve this complexity issue by making the model as simple as possible? So, our objective is also to make the model simple. We want simplicity. Let's think about the philosophical background behind this. Occam's razor, whose principle states that the simplest strategy that works is the best one. If you have a complex one and a simple one, and they both work equally well, the simpler strategy is almost always better. So in this case, we can take this principle and apply it to our machine learning objective. In this case, we don't want complexity. We want the model to be simple. That's how we prevent overfitting. So if our original objective is to make the risk or the loss, the measure of wrongness, as small as possible, our objective is to minimize that, make it as accurate as possible. Why can't we just minimize the complexity too? After all, we are trying to make it as simple as possible. So it would make logical sense for our new objective to minimize both risk and loss, and then simultaneously make complexity as small as possible, or make it as simple as possible. So instead of having the objective to be the minimization of just the loss, the empirical risk, r hat of beta, where beta is like our parameters, we can have that plus whatever our measure of complexity is. In this case, we have to minimize both the loss and the complexity for the overall score to go down. So now we have to minimize both. How do we define it concretely, though? We defined complexity, but what is complexity really? How do we define how complex a model is? Do we look at how expressive it is? First, let's define this notion, which is called regularization. It's about adding a complexity term to our objective such that we can minimize complexity or make it as small as possible in addition to our core objective. The goal here is thus to encourage simplicity, make the model as simple as possible, and discourage it from being complex. The complexity, mathematically, is the size of that weight vector that we have. So if we compile all of our parameters into one singular weight vector and take the magnitude or the size of that and square it, we can think of that as our first concrete measure of complexity. Note that in this case, beta represents the parameters we chose, like the internal knobs or the internal settings learned during training. For instance, the things that, think of them as the things in the brain. Now that we've defined it, you can take a look at the formula below. The squared magnitude given by the two lines is like the size of that vector. The bigger that size is, the more complex it is. And thus, we have to, if we want to minimize that, we want to make that part also as small as possible. So we're encouraging it to make that size of the weights as small as possible, i.e. make it simpler. This is equivalent to saying the sum of the squared elements of the weight vector. So a large weight vector, the larger magnitude of a weight vector would make that overall error very, very high, because it would make that term high. But if it's smaller, it balances it out and it becomes lower. So we can, in order to minimize the overall loss, we would need to minimize both the empirical risk and this new term, this new complexity term we described, to make it as small as possible. But why do we square it? You might have noticed that instead of taking just the raw magnitude, we square it. So why do we do that? Well, think about the scenario where our magnitude might be a negative number, for instance, -5, -10, or -102. That's equivalent to saying it's equally as complex as a positive 102, positive 5. But yet, when you put the negative into the term, just going back there, if we didn't have that square, then that would subtract from the overall error, subtract from the overall quantity, thus leading to a smaller loss. So it encourages the model to have a negativity bias, encouraging it to say, to minimize the loss, you have to make the weights negative. But we don't want the weights to be negative. We want it to be neutral to the sign. So to treat sign fairly, the penalty must be non-negative. Thus, we can take the absolute value or the squared value. The one we discussed before is called L2 regularization, where we use the square. That's one possible way to make it non-negative. The other way is L1 regularization, where we use the absolute value. It also works, but later we'll see which one to use and when. The unifying idea behind this is that we can see this as a balancing act. We now have to balance both minimizing the loss and minimizing the complexity, not just one or the other. So we want to make both small. If the loss is large, the complexity is small, that's not good either. If the complexity is large, the loss is small, that complexity term dominates, and the overall loss will be also very big. So what we want to do is make both terms small, both the empirical risk and the complexity as small as possible. That's the only way we can minimize that overall error. So the core question or philosophy behind this is whether a simple model can generalize better than a complex one, and we'll see this later. Let's take a look into the geometry of L1 and L2 regularization. If we graph this, L1, because of its absolute value, forms a diamond of shape. It's like a sharp, pointy diamond. But the problem with this is at zero, if the magnitude was 0, there's a sharp kink because the absolute value function is not differentiable at 0. Thus, we have to use subgradient methods, which I'll discuss in a future video, in order to make this differentiable in practice. L2 is smoother because we're using the squared. It's like a parabola in some way. So it forms a circle, and in this case, it's smooth. There's no sharp kinks or anything, just like L1. And thus, we can make thoughts about the behavior of them at 0. L1 forces weights to be exactly 0. This is called sparsity. L2 makes weights near 0. What's the difference? Well, if we set weights to exact zeros, that can be situationally a good thing, because if we have a data set of many not informative features and they're entirely irrelevant, they don't provide any value. If we set the features with no value to exactly 0, we're essentially eliminating them and forcing the model to focus only on the features that count. L2 sets them to near 0, so it's saying we keep them, but we just make it less important. So it's sort of like hard versus soft selection in a way, and sparsity. If you think about it, imagine you're renovating a house. Then L1 would be the strategy where you throw all your like unneeded items away and just throw them in the bin and just set them to exactly 0 and remove them. L2 would be keeping them in maybe like a storage area. So it's not entirely eliminating it, but focusing vastly like shifting the priority from them to other ones so they become insignificant. Elastic net is a synthesis of both ideas, where we combine both L1 and L2 terms. So we minimize the risk plus the L1 term plus the L2 term. So it combines the benefits of both. Okay, we've defined the core notion of reducing complexity. But how important is this complexity penalty for us? We know that different data sets have different levels of overfitting risk. If we just have a static notion of a raw term, for instance, we want the flexibility to control how important or how necessary this complexity factor is in each case. How do we know whether, because right now the risk and the complexity term are equally weighted. But what if it's not as important? What if the overfitting problem isn't as significant in one specific data set than another? We can add a hyperparameter called lambda. As you can see here, this grants us the flexibility to tune this and adjust it, increase it or decrease it depending on the nature of the task. If we make lambda smaller, then it gives less weight to that regularization penalty. It says it's not that important. Well, if it's larger, uh, then the penalty is stronger and we have to care more about complexity. Tuning this is crucial because it balances the bias variance trade-off. If we make it smaller, generally speaking, the lambda hyperparameter, it will make it the bias lower, but it will also increase the variance because we're not applying that much pressure to the overfitting problem. We're not countering as much as if it were larger. Because if it were larger, then it would decrease the variance. But generally speaking, it would also increase the bias because we're encouraging the model to be simpler and thus less expressive. The big idea behind this is the question, how do we balance both accuracy and simplicity? Not just accuracy or not just simplicity, how do we do both? Regularization is the realized engineering technique to doing this. Thank you.